evening. Welcome to the Graham Clark Institute Biomedical Engineering Advances series. My name is Catherine Stock from the Melbourne School of Engineering. The Graham Clark Institute is committed to using our networks to bring some excitement to the public, and that's what I hope this lecture this evening will do. This is our first public event in the Biomedical Advances series, and we hope that the series will bring some of the best minds of biomedical engineering to you and share their exciting ideas and research with you. And with that, I would like to introduce Professor Marco Viceconti. He is the Chair of Biomechanics at the Department of Mechanical Engineering in the University of Sheffield. More so, he serves as Executive Director of the Insignio Institute for Silico Medicine, and we'll hear some of that this evening. He's an expert in musculoskeletal biomechanics and the use of subject-specific modelling to support medical decision-making, and he's a key figure in the Virtual Physiological Human Project and serves as president of the VPH Institute. I've known Marco, I lived in Switzerland for 14 years, and I've known him, I think, since I was a baby PhD student there. And it's such an honour to welcome you here this evening, to have you visit Australia and to be able to host you. And in my mind, I've always looked up to Marco as the kind of leader that I respect, the way that he can lobby the community, really, to get behind the importance of biomedical engineering. And I think that we're going to hear some of that this evening, and I'm really very excited about it. So with that, can we put our hands together and warmly welcome Marco?
Thank you, Catherine, and thank you to all for being here today. I'm really flattered for this invitation. It is my first time in Melbourne, actually my first down below. I'm currently spending a short sabbatical in Auckland, and so Catherine very kindly said, "Oh, you should come over." And that was the excuse, but I've been knowing you in university for many, many years, and I enjoy the discussion and the collaboration with many of your member staff, so I was very keen to have this opportunity, so thank you again. Tonight I'm going to talk to you about something called in silico medicine, and I'll try to explain you to the best of my capacity what it means. It won't be an in-depth scientific talk. I will not go in any specialistic detail, but of course I'm being more than happy to take your question or to follow up through email if you have more detailed curiosity about what I'm going to say today. I would like to start with a personal perspective by explaining how my own personal research trajectory brought me to starting from a degree in mechanical engineering to end up leading at the Institute of In Silico Medicine. So my beginning was, as I said, I'm a mechanical engineer. Very early, at the really beginning of my research career, I turned my attention to musculoskeletal biomechanics, in particular orthopedic biomechanics. And quite early, I started to use computer models to try to predict things which were difficult to measure experimentally. This is one of my first papers. You see the date, and that means that I'm pretty old. Also because this was not the beginning of my career. And for some time, what we did was just using the computational mechanics that was available as developed for other domains in engineering, aerospace, etc., to try to solve, within the limits of these methods, problems that were relevant for orthopedics biomechanics. But then the problem started. So around 2000, I was asked to deal with this problem. So what you see here is a biplanar X-ray of the lower body of a 4-year-old child who had this area here affected by a bone tumor called Ewing sarcoma. The first thing you need to do in this case is to remove the tumor, which means that they had to cut away half of the femur in this child. Now, if this was an adult, you would replace this big gap in the skeleton with a prosthetic device, okay? But if you are a 4-year-old child, I can put you a prosthetic device, but the device will stay where the rest of the body grows, and there will be a mismatch eventually. So a fantastic orthopedic surgeon in the institute where I was working at that time in Italy developed a very extraordinary surgical technique where essentially they reconstructed the skeleton by using partially bone bank tissue, so essentially tissue from cadaver bone, and partially bone taken from another part of the skeleton and auto-transplanted there so that it could regenerate and grow. This again wouldn't work in an adult, but in a 4-year-old child there are so much osteogenic potential that actually it worked very well. That was fine. The real question was, okay, we've done the surgery, and now we have to start the rehabilitation. How much load can we allow on this child in order not to fracture the reconstruction? And it was a tremendously difficult question because this reconstruction had made the skeleton of the well, first of all, every child is different from any other child because of the growth. The reconstruction had made the left side different from the right side, but also as you can imagine, when you have to remove half of the femur, you also have to move all the muscles that attach to that part of the skeleton. So even the musculature in one leg became very abnormal, okay? So here we came out with this idea to develop a subject-specific model, okay? And we started to develop this technique where we do medical imaging, and then we perform measurements on the patient in the lab. Then we fuse this data and we use them to develop this computer model that can predict the forces being transmitted to the reconstructed portion of the skeleton during a rehabilitation exercise. But this was a recurrent thing because the more I went on with my research, the more I realized that every person is different. And we could not keep going with this idea of a population medicine. So if you're a woman, you're 50, you take this pill. Because everyone is different. I was not the only one to notice this. This is the number of papers published in the world about subject-specific modeling. And I started to look into this around here. So I was a little bit ahead of the curve, but not that much, okay? So nowadays, subject-specific modeling is becoming one of the leading themes in computational medicine. The second problem, big problem, that I immediately started to deal with in my early research career was scale separation. It's a bit complicated, it requires a little bit of explanation. But let me tell you, scale separation is the best trick that they teach you in the engineering school. It goes like this. So you're a mechanical engineer, you're supposed to calculate how much load this metal beam can take. Now, of course, the strength of this beam depends on the microscopical structure. And that would mean that in order to calculate the strength of the beam, you would have to know every single microscopic element, which would make this an impossible feat. But here comes scale separation. Because the biggest element in the microstructure of the steel, which is called grain, is about 60 microns, whereas my steel beam is about 6 meters, there are approximately 5 orders of magnitude of difference between this thing and this thing. And because of this, I can pretend I don't care about the microscopic structure and average it at the macroscopic scale. Okay? And this is what we call scale separation. And this is standard procedure in almost every engineering calculation. Every house, every bridge, everything we use every day is being calculated using this assumption because it works in engineering material. Now let me introduce you living materials. This is a human bone, a femur, is about 0.5 meter long. The largest microstructural unit, which is called osteon, is 1 millimeter long. So the scale separation here is only 2 orders of magnitude instead of 5. And this is not here. If you now look inside the osteon, there are other substructure, and surprisingly, they are also about 2 orders of magnitude smaller. There is this 2 orders of magnitude is recurrent in a lot of tissue in living organisms. What does it mean? It means that if I have to calculate how much load is required to break this bone, I cannot do this precisely without knowing something about the macroscopic structure. So that's forced me to describe the mechanical behavior of the body across multiple scales. Okay. So subject-specific, multi-scale, two big challenges. Again, my first hit with this multi-scale problem was a very specific orthopedic problem I was faced a few years after. This schematic picture represents a new medical device. It was a hip replacement. It was an anatomical cementless stem. The stem is the part that goes into the femur of a hip replacement prosthesis. It was a fairly innovative design, so the company wanted to know how big was the risk of having a particular complication known as aseptic loosening. Unfortunately, this complication is the result of a very complex mechanobiological interaction that happens at the organ level between the prosthesis and the bone, but also at the microscopic level between the cells and the tissue that differentiates in one good way or in a bad way, producing the success or the failure of the implant. Okay? And for the first time, in 2004, we published this paper where we were coupling a whole body model, a whole organ model, to a tissue differentiation model to predict the incidence of aseptic loosening. At that time, this was just a guess, and we predicted that with this design over general population, the risk of this complication would be 2%, which was considered acceptable by the company, and they proceeded to produce and implant this device on large scale. 12 years after, I went back and I collected data from the orthopedic registry of Italy that monitor all the hip replacement in the country and their outcome. And I found that this device had an incidence of aseptic loosening of 1.5%. So this to suggest that even this relatively primitive early attempts of predicting complex processes could be very accurate. While I was doing this in my own little field of orthopedic biomechanics, I had the opportunity at conferences around the world to talk with other colleagues who were working in completely different problems, in cancer, in cardiovascular, and surprisingly these two themes, multi-scale, subject-specific, were recurrent in the conversation. It looks like everyone was having the same problem in spite we were dealing with very different clinical challenges. So with the help of many colleagues in Europe, we launched this initiative called Seeding the Europhysium. The idea was to take an initial intuition that actually started here down below in New Zealand, the Physium project led by Peter Hunter, but decline it in Europe into a way to solve clinical problem. In 2007, we published this research roadmap where we proposed the idea of creating a framework of technology called the Virtual Physiological Human, or VPH for short. This is the definition we gave at that time. So in other words, the VPH was a framework of method and technology that once realized it would have made possible to investigate the behavior of living organisms in different subjects and across different space-time scales. So look at the human body as a whole, okay? The publication of this roadmap was very important because it created a sort of momentum around a territory that before was very fragmented. So we started to perceive ourselves as a research community, whereas before we were spread all over different departments and in different countries. The other thing is that thanks to this roadmap, we were able to convince the European Commission that this was a good idea to put money in. And so we started to receive funding for this area, okay? As all the funding is distributed in Europe, of course, it was competitive, so we all applied and some were successful, some were not. I was lucky, and one of the applications that I submitted was actually funded. And this was probably when you and I started to interact more frequently because at that time, Catherine was in ETH in the group of Ralph Muller that was one of the core partners of this project. So with 4 years, we developed extensively this idea of the VPH with respect to the musculoskeletal system. The goal was to develop what we call an hypermodel or a multiscale model that would actually go from the single cell up to the whole body. And the clinical goal was to predict the risk of bone fracture in fragile elders, typically patients affected by osteoporosis. It was a fantastic experience. I learned so much that I was actually able to write a book about the multiscale modeling of the skeletal system that was published in 2011. But that was also a time of crisis for me because I was in Italy. I was running what in Italy was considered an extremely successful research group, but for me it was too small. I felt that if we really wanted to tackle this challenge, we had to move to a grand science scale, create large research institutes with hundreds of academics coming from all different specialties that could collaborate together interdisciplinary. The early 2000s were not a good time for Italy from economical and social reasons. So such an ambitious project was not viable in my own country. So at the green age of 50, I decided to move. With the support of my lovely wife, we went in Sheffield. Now, if you ask where is Sheffield, this is a legitimate question. Is in England. It's not far from Manchester, which is probably slightly bigger. In South Yorkshire, this is the picture we use to attract students. But don't get fooled. This is Sheffield. So, Paula and I, my wife and I, lived in Bologna. I don't know if you've ever been in Bologna, medieval city, lovely weather, fantastic food. So at the personal level, that was an important choice. But at the professional level, this was the best thing ever happened to me. Because in Sheffield, there is a fantastic university with an amazing leadership. And with their support, I moved there in October 2011. After 6 months, we opened the Insignio Institute for In Silico Medicine. It was a joint initiative, it is still today a joint initiative between the University of Sheffield and the Sheffield Teaching Hospital, which again underlined the very strong clinical translation of this research. And it started from the beginning as the idea of something that would cut across department and faculty. It would be dramatically interdisciplinary, and the glue would be the goal, predicting the human body in a way that is useful for healthcare. And it was a success story, and it still is. This is the growth rate at 2 parameters. How many members? To become a member of Insignio, you have to be an academic of the University of Sheffield or a clinician in the Sheffield Teaching Hospital. So this is not including PhD students, postdocs, etc. Okay? And this is the funding that we were able to attract through competitive grants over the 6 years of existence of the Institute. So today Insignio, and these are the last figures from our annual report, is the largest research institute in silico medicine in Europe, and is second in the world only to the Auckland Bioengineering Institute, which is in New Zealand. I want to stress, today in Insignio work 145 academics or clinicians. They sit in 29 different departments. So we have the most amazing interdisciplinarity that you can imagine. One of our academics is a philosopher, and she is a specialist in the philosophical problem of investigating at the interface between biology and technology. And she is very useful, and she's doing a lot of collaborative projects with hard scientists, etc. Okay? So, you might think that an in silico medicine institute is a big room full of computers and a lot of nerds. Yes, we have plenty of nerds and plenty of computers, but there is a very strong experimental component. You cannot build and validate computer models without a systematic experimental research. You also need to collect a lot of detailed data on the patient that you want to build a model for. And that's why organic to Insignia is all the research in areas such medical imaging. We have one of the best MRI physics research group in the country. Deep sequencing for looking at genomic and post-genomic data. We also have very special imaging facility to investigate animal models, and a lot of clinical quantification, a lot of biomedical instrumentation that we install in the 2 hospitals in Sheffield, which we use to measure systematically patient enrolled in clinical trials from a physical, electrophysiological, cardiological, respiratory way. We have 3 gate labs, 2 in the 2 hospitals, in the Children's Hospital and the Adult Hospital, and a 3rd led by Claudia Mazza is a research clinical gate lab where we develop the protocols. And then we have a number of experimental laboratories, some like this one, very similar to one I visit this afternoon here. And these are absolutely organic to an in silico medicine institute. If you happen to be around Europe, you may consider yourself invited to our annual showcase. This is something we've been doing now for 4 years in a row, and it's becoming a sort of an event. Typically there are between 200 and 300 delegates. It's a one day, we show everything we do to our friends, our partners, our funders, our industrial partners, and it's also an opportunity for all these people to show what they have, what they do, the new technology. It's becoming a sort of a fair of in silico medicine, and it's very exciting. The next is May the 3rd, and as I said, if you happen to pass by Europe, please consider yourself invited. So, I told you about this in silico medicine institute. What is in silico medicine? What does it mean exactly? Well, I challenge the notion that medicine is fundamentally about predicting. So you're a doctor and you have a child in front of you who has certain symptoms. How do you decide what to do, how to treat her? Well, essentially you do 2 things. You look in the existing knowledge that you have accumulated in school and then in continuous training, reading publication, etc. But in many cases, even more important, you also tap in the experience, your personal as a clinician, or the experience that is being shared by other clinicians, that when they had a group of patients that had similar symptoms, and this patient were treated in a certain way, those patients got better. And so by analogy, you provide the same treatment. And in doing this, you are predicting an outcome, okay? That is ultimately to be proved, which many, many times is correct. Sometimes it's not, and then the therapy has to be changed, adjusted, or even sometimes we change the diagnosis. It's a dynamic process. Now, what makes this process incredibly challenging is that starting from the ancient time through the traditional medicine, still through the 19th century revolution, and still today in most developed countries, a doctor has to take this decision with not enough information. In fact, we train doctors to take decisions without all the necessary information, because that's what they have to do historically. So it is a bit of a paradox that instead, if you're a specialist working in developed country nowadays, you have the opposite problem. The development of medical imaging, of sequencing technology, the automation of laboratory analysis that now makes possible to do 100 different tests on a blood sample for a few pounds. The incredible development of biomedical instrumentation, all this technology are generating enormous amount of information about the patient that the doctor doesn't know how to use at the best. And in fact, most of this information are not used in the clinical practice, in spite of being available, because we don't know what to do with it. So what is predictive medicine? Predictive medicine is the ability to make this need for prediction that is built into medicine a more systematic process based on the abundance of information that makes possible through computer simulation to fuse all this information about the patient and make reliable prediction. Until now, in order to make prediction about things that happen in the human body, essentially we use two approaches. One is called in vitro, which means that we are studying cell cultures, essentially, or tissue culture. And the other is called in vivo, which means we are looking at living organisms, either clinical trials, where the guinea pig is the patient himself, or in animal model, in animal experiments. Okay. We propose there is a third way that, for analogy, we call in silico. Silico comes from silicon in the computer chips, which is another way to develop this predictive technology. But of course, and we go back to where I started from, in order for this to be possible, first we have to be able to build reliable prediction, and this comes only from the ability to produce computer models which are subject-specific and multiscale. And that is where in silico medicine really stays, in the ability, in the technology and the knowledge to develop patient-specific, subject-specific, multiscale model that can predict quantity which are relevant for the clinical practice. Where do we use in silico medicine technologies? There are three broad areas of application, and these are defined by who is the end user. So the first is called digital patient, and the end user is a doctor. Typically, the prediction that come out of the model are used by a specialist, typically in a secondary care setting, so in a hospital, to decide the best course of action for a patient, for a given patient in front of the doctor. The second, more recent, is called in silico clinical trial. Here, the computer model are not used to decide something about an individual patient, but rather to decide if a new drug or a new medical device are safe and or effective. And the third, which is really emerging only now, there are the first pilot coming out now, it's called personal health forecasting. Here the end user is the citizen patient. And the application we imagine are technology where a patient with a chronic condition like diabetes type 2 can use this technology to better self-manage daily his condition. So let me give you some in-depth view to each of these. The digital patient. Last year, Civitas, which is a think tank in UK, engaged a number of people who are listed here, specialists in very different areas of social and sciences, about a fundamental question. How can we salvage universal health care? I don't know if you know, but the term universal health care indicates a healthcare provision model where if you are a citizen of that country and you're sick, you go and you get the best possible care, no question asked for. Okay? This is the dominant healthcare model in Europe. It is the dominant healthcare model in UK, but this healthcare model is being challenged and is becoming more and more difficult to sustain universal healthcare system. And so they contacted a bunch of people and they say, well, from your point of view, from your specialism, legal, ethical, social, technological, how can we salvage universal healthcare in UK? And this book that you find online is publicly available, is the summary of this opinion piece. I was flattered to be invited to be the expert for technology in this exercise. So my analysis was this one. We have two problems in Europe, in UK, but in almost every developed country nowadays. The first is very well known and everybody's talking about it. It's called the aging population. In short, more people continue to live than children are born, so the average age of the population is growing, okay? But there is another problem that nobody mentioned, or very rarely, because ultimately it's not a problem, it's a good thing, but it turns out as a problem. In the last 50 years, thanks to the amazing progress of medical research, a number of pathologies that were lethal were transformed in chronic diseases. Perfect example is a number of oncological forms that 30 years ago you would definitely die within 3 years. Now you can live 20 years, but you're not healthy. You need continuous care and monitoring and attention, okay? So you're a chronic patient. These two things together are creating a burden of care which is incredibly hard to sustain economically and organizationally. How this relates to predictive medicine? Well, the first thing that came out for the fact that the average age of our patient is growing and that a lot of disease, instead of killing them, they remain in a chronic form, is that the number of patients that come in a hospital every day being affected by 2 or more diseases is growing exponentially. This is a huge problem because almost everything we do in medicine is based on the assumption that you are a healthy person equal to any other healthy person except one thing, that is the disease you have. If you have 2 diseases, we are screwed. We don't know what to do. Why? Because at that point, each patient becomes a completely different story on his own. Because which 2 diseases you have, and what about if there are 3, and at which stage, how they interact together. So the need for a much more personalized medicine, where you see the patient for whoever he is, with all this disease and condition and ongoing treatment, and you decide, taking this big picture, for the best course of action. In themselves, chronic conditions are very difficult to handle effectively because they accumulate an enormous amount of expensive care. And it's being proved that the best way to deal with chronic condition is to avoid them. So, prevention. But prevention is very challenging. Everybody talks about prevention, but in practice is incredibly challenging. Here I always have a problem. In Italian there is a beautiful term which is accanimento terapeutico. It does not translate properly in English. I think it has to do with the culture behind our being Catholics or whatever. The best translation I found is futile care. What I mean is there is a point sometime in the therapeutic history of a patient where the doctor and the patient have to agree that it's time to die. That it's time to manage the residual quality of life, but not trying to fight the disease because the battle is lost, okay? This is an extremely difficult decision to take because this decision can be taken only by the patient, ultimately. And in order for the patient to take this decision, you should be able to go to the patient and say, well, look, this is the situation. If we continue to treat you, this is what you can expect. If we stop to treat you, this is what's going. So we need to be able to make predictions which are highly reliable. And because we cannot, we usually keep treating, even when it's become clearly unnecessary and the suffering is the only thing we can deliver. So in order to bring in participation, which is the key element for this changing model, we need to solve this problem of being able to predict. So all this is not my idea. Many people have been suggesting, probably the more loud in pushing for this vision that he called the 4P medicine is Leroy Hood, when he founded many years ago his Institute of System Biology. Why 4P? Well, because the first is predictive. If you can improve our ability to predict, you can imagine a more personalized healthcare, a more preventive healthcare, a more participatory healthcare. So the first P enabled the other 3. So that's what we are trying to do in Sheffield. Let me give you some example. You don't feel well, chest pains. You go to the doctor and they say, oh, I'm sorry, my friend, you have a coronary stenosis. The coronary are blood vessels that wrap your heart and essentially bring oxygen so that the heart can work and pump. If not enough blood arrive, the heart starts to starve and it cannot work. Okay? And ultimately you can have a heart attack. There are different treatment options, and it's being proven conclusively. Every clinician agrees that the best way to decide how to treat a patient that has 1 or 2 coronary stenosis lesion like this is a measurement. It's called fractional flow reserve. It's an invasive measurement. Essentially, you introduce a pressure sensor through the circulatory system until the vessel, okay? It's expensive, it's risky, and only in a few hospitals there is the instrumentation and the skill to do this test. As a result, in spite of the fact that everybody agrees this is the best practice, today in UK only 5% of the coronary stenosis patients are treated on the basis of a FFR measurement. We had this idea. If we can take these images of the lesion and use them to build a patient-specific model that can predict non-invasively FFR, we can get the same thing without producing any invasiveness. This picture can be produced in virtually any hospital who has a cardiology department. So you don't need special things. It's very cheap, it's very fast, non-invasive. So we're replacing an expensive invasive measurement with a non-invasive one based on prediction. Here, we're trying to do something similar but much more complicated. At the top of the heart, there are 2 structures that are called heart valves that makes possible for the heart to pump the blood in the right direction and prevent that the blood goes back, okay? They are essential for the heart to work as an efficient pumping machine, okay? Unfortunately, they get diseased. And when they get diseased, the efficiency of the heart starts to decrease. And beyond a certain level, we get very, very seriously ill. Again, there are many treatment options nowadays to repair or reconstruct or replace valves. But the doctors are kind of left alone to decide for every patient what is the best way to choose the treatment. In the UrValve project, a team of 15 institutions are collaborating to develop in Silico medicine strategy to personalize the decision based on all available information for that patient. I said at the beginning, sometimes getting the information out of the patient is really the point, the difficult thing. My colleague and friend Jim Wild is a fantastic MRI physicist. And Jim has had this amazing idea. You take a noble gas. A noble gas is a chemically inert gas. You can breathe it, it has no effect, completely passive. But with a special laser, you can polarize the molecules of this gas. And after you polarize it, using very special hardware, you give this gas to the patient, so the patient breathes it with a mask, of course mix it with oxygen, etc., so he has no physical effect, while he's being scanned by an MRI. This gas acts as a contrast agent. So for the first time, you can see in the MRI, with absolute detail, the anatomy of the lungs, which until recently was impossible. But more, we can trace the gas as it permeates in the alveoli and goes in the blood system, so we can calculate the efficiency of the oxygen exchange between the lung and the blood. So this is opening a whole world of applications. But one I want to mention, because I'm particularly proud of this, and the reason is that this very complicated disease called pulmonary hypertension, for a reason that nobody knows, has an extraordinary prevalence in South Yorkshire. In South Yorkshire, there are more PH patients than anywhere else in UK. We don't know why. Probably that area has a long history of pollution, with steel mills, coal mines, etc. So probably there is an environmental determinant. What is pulmonary hypertension? Well, that's the beauty. It's not a disease, it's a syndrome. Essentially, the vessel that connects the heart to the lung start to function at an abnormal high pressure. But this could be due to the heart, to the lung, or to the vessel. So the doctor has to do a differential diagnosis, first of all, and identifying where is the primary source of the disease. And again, guess what? In order to make this differential diagnosis, you have to make an invasive measurement, except that this time you have to stick a probe into the heart, inside the heart, through the pulmonary artery and into the lung. So essentially, you never do this, okay, because it's so dangerous and complicated. And with this new technology that Jim have developed, together with Andrew Swift and Rod Hose, our modeling specialist, we can take the MRI data, non-invasively predict the wave reflection between the lung and the heart, and make a reliable prediction of where is the disease, and use this to guide the medical decision. Back pain. I think 50% of the people experience back pain at least once in their life. So this is not a disease, it's a pandemic, okay? It is the primary cause of work loss in all developed countries, in all industrialized countries. And again, once you have back pain, depending on how exactly is your condition, there are three possible options. Conservative treatment, a very aggressive surgical procedure, and an intermediate surgical procedure. Damien Lacroix in the MySpine project has developed a patient-specific modeling technology that allows to classify correctly the best treatment for each patient between these three options. This has already been tested on over 200 patients and works flawlessly. CT2S, this is my own project. I've been working many years on this, but now it works. We have a technology where we can take a CT scan of a region of the skeleton of a patient, and I can tell you what is the force that is required to break the bone of that patient. And with this bone strength information, I can estimate the risk that you have of having a fragility fracture because you're falling. So we got excited and we start to look at more challenging problem. And not surprisingly, a lot of challenging problems come in the pediatric field. And this somehow brought me back to the beginning of my career when I had, you remember, this very challenging pediatric problem. There is this incredibly weird disease called juvenile idiopathic arthritis. And again, for those of you who are not expert in medicine, idiopathic means I don't have a clue of what is causing this disease. It's a magical word the doctor used to express our ignorance, okay? It is non-rheumatoid, so the rheumatoid markers are negative. It manifests with the symptom of an arthritis. It affects only children and is incredibly heterogeneous. So both in terms of severity, some have all joints affected, some only have one joint. But the most important heterogeneity from a clinical point of view is the response to the first line treatment. How about half of the children respond very well to a mild anti-inflammatory therapy? The other half don't. And for them, we have to use incredibly aggressive therapy. But the problem is that if we would know from the beginning, we would not waste 6 months trying with a mild therapy, and we would probably spare some damage to the joint. Okay? So it's very important to understand which one will respond to the therapy and which not. This is a very long story, but to make a short, long story, I think we spotted the primary reason for this difference between responder and not responder. And we did this because of subject-specific modeling. The last point, it's very useful in a number of situations to know how much force you need to break a bone. How do we know this? Well, because people, very generous people, donate their body to a science program, and we harvest bone from this cadaver, and we break them, and we measure this force. Of course, no one donates children's body to this program, very understandably. So there is absolutely no knowledge of what is the force required to break the femur of a 2-year-old child. Why would we care? Because a poor radiologist in a children's hospital almost every day has to decide if that fracture was really happened because the child felt or because there is an abuse. That's a very tough decision, trust me. And without any scientific evidence is even more difficult. Of course, there is a lot of clinical experience, but every child is different. That's the other problem. So experience falls short. So we had this fantastic idea. We can use our technology to look at this post-mortem. So in the Sheffield hospital, we convinced a number of families to allow us to perform a CT scan to the body of their children. Of course, this doesn't touch the body, it doesn't violate the body, so the family are much more available to allow you to do this, okay, because essentially no damage is done. And then we use this CT scan data to estimate the strength of bones in children, especially in infants from 0 to 3 years old. And we have now published the first reference table that, based on the age and some essential measurement, can tell you order of magnitude of the force that is required to break a certain bone in a child of a given age. Okay? And this will be an essential tool in the hospital, but also in the courts during litigation to decide what is what, ultimately. Okay, so this is digital patient, very developed. I told you that in silico clinical trials is emerging only now, and the reason is explained here. So this is how much it costs to bring a new drug to the market. It's ridiculous, $2.5 billion. It's killing innovation. In fact, this went up. In the meanwhile, the rate of innovation went flat. Because and you know, if you have a rare disease, goodbye, because how are you going to recover $2.5 billion in a disease where you have 100 patients? Well, now there is an interesting trend. You know that there is this new therapy for very rare disease that are offered at $1 million per treatment. So it's a crazy situation. And why is it so expensive? The primary reason is the incredible cost for the regulatory process. Now, let me tell you one thing. I am an engineer. I designed a new large carrier, a new airplane. Or I just finished to design a new nuclear power plant. How would you feel if I tell you, in order to make sure that these are safe, I'll make a few copies, put them in use, and if they don't blow, they are safe? It's crazy, no? Well, that's exactly how we test drugs and medical device. We make a few copies, put in some patients, see what happens. How do we design this? With computers. Before the first part of this complex system is built, hundreds of computer simulations are run to test all possible scenarios, okay? And only then, when we're reasonably sure of the safety, we go on and start to build, okay? Why is not being used? Because let me be very clear, until 2 years ago, it was not allowed anywhere in the world to use a computer simulation to produce an evidence in a regulatory process of a medical product. So, again, I rolled my sleeve, and together with a number of colleagues, we started to lobby. And we wrote this document, which contains very strong evidence that this is a very bad idea for everyone. And we convinced. So, between the end of 2015 and beginning of 2016, both the US Congress and the European Parliament made very similar recommendations to their regulatory bodies, saying you must use modeling and simulation, okay? And this is now starting. And I expect that this will become the big deal in silico medicine in the next few years. In the meanwhile, we have an early impact, which is relevant from a social point of view. I don't know in Australia, but in UK, animal experimentation is being more and more perceived as an unethical practice in many regards, okay? Well, what we're doing in Sheffield is to use this type of VPH technology to reduce animal experimentation. In this study, for an animal model for bone drugs, we were able to reduce the number of animals enrolled of 60%, okay? So considerably reducing the animal experimentation. But there is a future here, and now we're working on this. Out of 5 drugs that pass the preclinical testing on animal, 4 will fail in the clinical trial. It's pretty bad, eh? It means the 4 times out of 5 animal models don't work. So my dream is actually to use VPH technology to being able to translate what we're seeing in the animal in what will happen in the human, so that the very few animal experiments we must do are really useful, and we need to do also less clinical experimentation, okay? Good, the last point, personal health forecasting. I can talk about this in many ways, but I chose to use it with a very peculiar angle, which is developing country. It is estimated that by 2020, 65% of the human population will be covered by a 4G network, and more than 90%, regardless where they are in the world, by some sort of cellular network. So it is reasonable to assume that even people who live in very remote locations can in principle be reached by cellular communication. If you look at the consumer electronics industry, in the last few years, there has been an emergence of all this type of devices, which are used to monitor the health status of people. This family of devices have two characteristics. They are designed to be used not by a doctor, so they are easy to use. And when they are produced in mass number, they are incredibly cheap. So you are in a rural village in the north of India. The first hospital is 2 days' travel from where you live. But you can deploy a nurse, a mobile cell connection, and some of this very low-cost instrument. Under the guidance of a remote doctor, the nurse locally can perform a series of measurements and tests, transmit the data remotely, and with this data, the doctor can decide what to do. Most of the time, recommend the nurse on the intervention. In the very few cases, organize the transport to the remote hospital. What is the problem? The problem is that this sensor that I show you usually give you only a piece of the information that you need to take a clinical decision, but not all. Here's where our technology comes in. We are developing patient-specific models that, when they are combined and added to the sensor information, give you the full range of information. So, for example, imagine that you have a lesion in the aorta that, if it grows beyond a certain level, could rupture and you die. But it could not grow, so they send you home. Normally, every 2 weeks you would go to the hospital being checked. But if you live in a remote village, this is not going to happen. But I can give you a device like this that costs probably 50 pounds, that does a single channel EEG on your mobile phone. Alone, this is not enough, but if you combine to a subject-specific model, you can probably estimate how the aneurysm is progressive, so that when it's time, when you're starting to get at risk, we call you back in the hospital and operate. I am at the end of my presentation. I tried to give you a view of what in silico medicine is, and when I started to do this type of public communication around 2007, very frequently, not from the people, but from the specialists, the reaction was, yeah, but this is science fiction. Yeah, it will happen probably in 50 years, 30 years, you know, but not tomorrow, okay? And to be fair, three recent studies showed that the average time between research discovery and full clinical adoption for radical disruptive technology is about 17 years. So not 30, but 17 was a reasonable average time, no? Well, in 2014, our first VPH product was fully commercialized in the world, the HeartFlow technology. And today there are probably a dozen of VPH products available in hospitals all over the world. And funny enough, now we're criticized by saying, oh, but where is the clinical impact? Come on, guys, we just started. I'm saying this because frequently this technology call for polarized reaction. No, it's not going to happen. Oh, why it hasn't already happened? The truth is in between. It is happening. So, in conclusion, I believe that in silico medicine is transforming healthcare, enabling for the first time a concrete 4P medicine vision. This new opening of regulatory pace based on in silico in the US and the European regulatory body is creating a new whole territory for the de-risking of medical products. And the beginnings are always difficult, so the introduction of the first VPH technology is being very challenging, but I see every day it's getting easier, so I expect the adoption to become exponential. I would like to acknowledge all my colleagues and co-workers, all the funding source, and thank you very much for your attention.
Thank you very much, Marco. Does anyone have any questions for Marco? A million questions for Marco? We'll take one here.
A question about prediction with respect to when you start using computational systems in prediction is that you can predict various outcomes in medicine. You can predict longevity, you can predict costing, you can predict quality of life. When the computer starts to take over that decision making, where does the doctor stand? How do you decide which decision is right? And how do you build that into in silico modeling?
That's easy. In the same way you decide what to do with any instrumental measurement. There's no difference.
But do you think that there will be a situation where you build your model based around, let's say, survival rates? But
No, I'm sorry. Okay, here maybe there is a misunderstanding. The model I'm referring are not statistical models. These are model based on the physics, the physiology. So we don't predict survival rate, which depends from everything. We predict the pressure in the blood vessel, or the probability that that vessel rupture at a given point in time because of that pressure. So, and these are usually things that in special condition can actually be measured, so we can test how accurate our predictions are before we use it in the clinics, okay?
do you predict the intervention as well, or it's mostly pathological?
No, there are models where you simulate the effect of the intervention. They are more complex, but yes, this sometimes is essential. For example, when you need to decide if you have two interventions, which one is the best for that patient.
And how do you decide which is the best intervention? Just finish that one up. How would one of those models decide what is the best form of intervention?
That's one of the reasons why this field must be highly interdisciplinary, because no engineer or computer science could be this alone. So typically, we start in a team where there are clinical specialists. We identify what is technically called an endpoint, which is one or a set of quantities that are proven useful to take that decision, and then we focus in predicting that quantities.
How fast is your VIRTUheart calculation?
Very fast. It's a 1D model.
A 1D model.
And more important, we have now developed a surrogate modeling techniques which we lose less than 1% accuracy, and it brings the speed to real time. So no, that's not the problem in that particular. In other problem, yes, I'm not saying in general, but in the FFR, the VFFR is really fast.
Can you expand on these surrogate techniques that you just mentioned?
I think they use NARMAX. It's a nonlinear system identification. I can send you the detail. It's not my own research, it's in my institute, but if you drop me an email, my email is available on my homepage at the university. I'll be delighted to point you to the author and the papers.
Yeah, thank you for the talk. These subject-specific models, by experience, are very time-intensive to build. And what sort of approaches do you do to cut down that time-intensive?
That's a good question. They are time-intensive because we do it in the most stupid way. All of us, it's a worldwide problem in the sense that we go in a picture and click one by one every pixel to segment, things like that. So we do two things. The first, once we proved the efficacy, so once we say, okay, this is going to work, there is a new research line to become an engineering research line. So how much can I automate, okay? Or how much can I parallelize? How much can I replace with some surrogate or machine learning or whatever? The other thing is order reduction. Do I really need all those information to have an accurate. So at the beginning, we usually try to get as much as we can. Once we have a validated high-order model, we try to see, so for example, say that the segmentation of the muscle in the MRI, it's time-consuming. Can you get away with that? Can you replace it with a distribution of average size? So how much you personalize also is a variable. You understand?
Has any of this work been applied to any of the cancer aspects, cancer symptoms?
Modelling cancer.
Oh, cancer. Okay, sorry. We're not very good in Sheffield about that, to be very brutally honest. I wish we were better. We have a couple of people who are working in what is called computational oncology, but we are not the best group in the country or in the world. But there are groups who are fantastic. I mean, so yes, in general, it is being applied. In particular, the enormous potential I'm seeing is, so take breast cancer, for example. Okay, the big revolution of the triple R. We had this fantastic discovery that if you look at the mutation in the cancer tissue, you can decide whether one of the therapy will work or not. You know, so you identify the women who are resistant. Okay. Now all this works around very early stage cancer, when the solid tumor is confined, it's quite homogeneous in terms of mutation, cellularity, etc., and is not vascularized. What about other, advanced stage? Well, that is a mess today. And the reason is because you have three processes: the growth of the cancer, the continuous mutation and differentiation, death, apoptosis of the cell. So the tumor becomes not one cell describe all, but it becomes a very heterogeneous organism. And then there's this magical thing that they start to build their own blood supply, the bastards. And that changed completely the game, because suddenly they can get as much energy as they want. Now, multiscale modeling can deal with this level of complexity, and that's where I'm seeing computational oncology really shining right now.
I was wondering about the link to genetics.
Almost there. There is a concrete problem. We are very good in modeling up to 1,000 atoms. It's called molecular dynamics. So you can build computer models that predict. Actually, some years ago, a Nobel Prize of Chemistry was given to the guy who invented these techniques, because really it's incredibly effective, up to, say, 1,000 atoms. Then there is a gap, and then the best model we have work at a single cell. So there is this territory, no? You agree, Catherine? Between the atomistic scale and the single cell scale, there is currently a gap. But there is a lot of very smart people that are looking to it on both sides. So it's like a bridge built on, I hope we don't end up like this, but I'm joking. No, I can see, it is a problem today. I admit, honestly, it is a problem, but I believe that in 5 years' time, this bridge will be made. And then it will be huge. Yeah, it will be huge.
Thank you so much for a fantastic talk. My name is Graeme. I originate from the Netherlands. And I've got a good friend at the TU Eindhoven. I've seen that you've worked with them, which is Professor Annelies van Bronswijk, who studied and lectured a long time genome technology, why people die. She was a terrible fighter to get ducted systems banned, and we have a bit of a problem in New Zealand and Australia with that same issue.
Okay.
The US distributes energy with air, and Denmark and Sweden do that with water. I don't know the situation in the UK, but here you see all these vents in the floor. They distribute air and distribute bacteria in environments. Professor van Bronswijk got them banned in the Netherlands. Are you able to make such a similar link like she did successfully in the Netherlands with energy distribution and why people die? Because we've got the highest asthma levels in the world, in New Zealand and in Australia, and that needs to be fixed on a plumber's level, not on a medical level.
It's a very good point. Thank you for this question. I have to admit that I don't think we're harvesting this potential opportunity as much as we could. So currently there is no one in Insignia who is doing this type of research. But I do recognize that this approach that I described, because it has the ability to model quite accurately systems for which we know the physical laws, would be extremely effective. And I'm familiar with the work you're referring to. And you know, the trick was the ability to model this flow system, the bacterial transport, and then of course how this would affect the epidemiology that this brings, okay? But the environmental part can be modeled computationally with very, very good level of detail, okay? And the same applies to more complex environmental, you know, environmental computational science are incredibly advanced. So there are computer models for UV radiation, for the temperature, for the humidity, etc. So the idea of coupling these models in order to do much more advanced exploration of how human activity through the environment affect human health, it is very interesting. I think you're right.
Well, with that, we'll call it a close. I want to thank everyone for coming, for your questions, but mostly I'd like to, and please join me in thanking Marco for